Okay, well, I hope you guys are still with me here on the next one, the psychopharmacology front. Let's see, we're going to start off with some basic terms. You could take a whole semester of psychopharmacology. Psychopharmacology, to me, is the most interesting part of this whole equation, and the reason we covered the others was to see how it mapped to psychopharmacology. In the field of psychopharmacology, we see how drugs affect behavior. Psychopharmacology is the study of how drugs, pharmacology, affect behavior, the psychology. Most of the time, psychopharmacologists work very closely with neurochemists because when you take a drug, it affects that process that we just went through in terms of neurochemistry. So, we're going to learn a little bit about this. We're not going to learn everything about this. That's going to be a little bit more on some of your own searches, but we're going to talk about some basic terms here and learn about 2 or 3 big issues. Okay, first, terms of agonist versus antagonist. A drug is considered a chemical outside the body, an exogenous chemical, if you will, a chemical from outside the body. I don't know if I could spell exogenous for you here. E-X-O-G-E-N-O-U-S. A drug is something from outside the body. So, for example, let me give you an example of something that would be an agonist versus an antagonist. An agonist is a product that basically mimics the neurotransmitter. It acts just like the neurotransmitter. An antagonist, on the other hand, is something that blocks the effect of the neurotransmitter. Blocks the effect of a neurotransmitter. Let me try 2 new ones on you. You may be familiar with neurotransmitters called the endorphins. Have you heard of these before? The endorphins? E-N-D-O are endorphins, P-H-I-N-S, the endorphins. Well, it turns out that a product that's considered an endorphin agonist is morphine. When you ingest morphine, when you take morphine, it acts just like the endorphins in the brain, and thus you'll feel no pain. And by the way, it'll work in an area of the brain called the periaqueductal gray. That's where a lot of your pain receptors are. So morphine is considered an agonist for pain and an agonist for the endorphins. If you've ever taken something called Narcan, N-A-R-C-A-N, it actually acts like an antagonist. It'll block the effects of morphine. Sometimes you get that for people coming into a hospital for a heroin overdose. It blocks the receptor and can save their lives, actually. So anyway, agonist versus antagonist. So I'm going to go over a few examples of this, and basically the idea is, do you remember all the steps we just mapped out with neurochemistry? Synthesis, storage, release. All of these outside drugs that we take can actually affect different parts of this process. So let's start with the first one. Let's say it's an example of somebody has Parkinson's disease, like my father. Turns out he has Parkinson's disease, and he takes something called L-DOPA. L-DOPA is considered a dopamine agonist. L-DOPA is a precursor to dopamine, so when they give my father L-DOPA, L-DOPA will be synthesized into dopamine right in the substantia nigra, right in the brain, and that'll end up being dopamine so that my father can have better motoric functions. So L-DOPA would be considered a dopamine agonist. On the other hand, if you know people who have schizophrenia, one of the theories in regards to schizophrenia is that there's too much dopamine working post-synaptically. Remember the idea of the postsynaptic region? The neurotransmitter binds and then causes an effect. Well, one of the hypotheses for schizophrenia is there's too much dopamine binding and being activated. And so you take a product like Haldol, H-A-L-D-O-L, or clozapine, C-L-O, clozapine, can I even spell it? C-L-O-Z-A-P-I-N-E. Those are both considered dopamine antagonists. They will bind postsynaptically and simply block the channel. So nothing ionotropically, nothing metabotropically. So an antagonist can bind and block the channels. So you've got agonist, you've got antagonist, amphetamine. People familiar with amphetamine? Amphetamine, when people take that, causes the release of norepinephrine and dopamine presynaptically. They actually increase the release of norepinephrine and dopamine in terms of exocytosis. When you take these products, the release, how much dopamine and norepinephrine that is released right at the end of the presynaptic region, is increased. So don't think that actually having too much calcium and too much dopamine, there's a balance here. Just having more is not necessarily better. So L-Dopa, clozapine, amphetamine, these are some of the products. Prozac. Turns out that Prozac is an interesting product. When you take Prozac, it turns out that depression is related to having not enough serotonin. And so Prozac is considered, as most of you know, a selective serotonin reuptake inhibitor. Isn't that a lot of fun? SSRI. What that basically means is when you take Prozac, when serotonin normally binds, it becomes inactivated via reuptake. And Prozac blocks it being taken back up. So Prozac keeps the serotonin in there longer. It increases the amount of serotonin. So actually Prozac is considered a serotonergic agonist. It increases serotonin amounts and thus helps out with depression. So that's one of the therapies that we know for depression. Maybe a final example for you. Well, there's so many examples, and I used to experiment with all these in graduate school in terms of rat pharmacology. But there are a lot of different examples, and one of the things I'd like you to do is when you look up the drugs that you've decided on for depression, see if you can find out about its psychopharmacology per se. So hopefully this makes sense to you. This is my little background here, agonist, antagonist, and so forth. I have one more big issue to kind of cover here. The one more big issue has to deal with a very important issue. It's called receptor subtypes. So the way I'm going to do this for you is I'm going to try to give you a specific story here and then kind of link the story back to kind of the key points at the end. So this story is going to start with a neurotransmitter known as acetylcholine. Are you all familiar with acetylcholine? It is a neurotransmitter. It works with a lot of different things. When you dream in REM sleep, it seems to work with that. It's very much right at your muscles. It's considered at a spot at your neuromuscular junction, so it makes you move. So acetylcholine is very important in your heart as well. And we're going to start our story with acetylcholine. Of course, how do you get acetylcholine? Well, you take an acetyl group and you attach it to a choline group. That's a little organic chemistry humor. You can just consider that extra after an hour of these lectures. Okay, so what they found is that when they gave acetylcholine, what scientists did a number of years ago is they set up some plates, some petri dishes, and they found that when acetylcholine binds, it seems to bind at receptors postsynaptically, and these receptors looked different. So basically what happened is that they found that acetylcholine seemed to get bound at two different types of receptors. And they started doing some more follow-up experiments on this. And they had these little dishes, and into one dish they had, let's see if I'm going to do this right or not. This is kind of exciting. Into one dish they put a substance called nicotine. You're all familiar with nicotine. They put nicotine into both of these dishes that had both of these different shaped receptors. And it seemed that for one of the receptor types, the nicotine, when it was put in, really was really attracted to the receptor, really got bound well. So we would say that the nicotine had a strong amount of efficacy for the receptor. It got bound well to this one type of receptor. When nicotine was put in this other dish, it did not get bound very well at all. So they decided to call this one type of receptor a nicotine subtype. So it seemed as if in this particular situation for acetylcholine, when you put nicotine into this particular dish and this particular substance, these receptors, it got bound really well. So they started calling this a receptor subtype. For acetylcholine, it seems that one receptor subtype is called a nicotinic receptor subtype. That means when you put nicotine into this these receptors, it'll get bound really well. It'll actually bind to the receptor very, very strongly. They also found that at the same time where nicotine actually does that, if they put curare into the same petri dish, if you will, that it would actually block the nicotinic receptor. So they basically found that nicotine got bound really well. It was considered an agonist at this receptor, whereas curare was considered an antagonist at this receptor. So this receptor subtype was called the nicotinic receptor subtype. So it seems one type of receptor where acetylcholine will bind will be this nicotinic one, but if you actually have nicotine, if you smoke a cigarette, it'll get bound, it'll bind really well to this nicotinic receptor and cause a lot of biological activity, and curare will block that. Into another type of receptor, this other dish, basically this other dish had another type of receptor in it, and when they put the nicotine and curare in this other type, there was not a lot of binding. Those chemicals didn't bound really well, so it was like these receptors don't work for that. But in this other dish, they put muscarine. And muscarine is a substance synthesized through mushrooms, if you will, some of the magic mushrooms of the 60s. And they found that muscarine got bound really well to these other receptors, not so much to the nicotinic, and that atropine tended to block the effects of muscarine. So they named this receptor subtype the muscarinic receptor subtype for acetylcholine. And if you're wondering why the heck I'm sharing this with you, and certainly I'm babbling along here and I haven't done quite as good job as I wanted to, it's very interesting. I've actually printed out, and if you go to some of these Wikipedia sites, there's actually some very interesting stuff going on and some really important issues with receptor subtypes. Let me give you the kind of the big issue here. Receptor subtypes is a huge topic in the study of neuroscience because there's a sense of the following. If you can make a drug that just got bound to one of these receptors, maybe you could fix problem behaviors and not have all the side effects associated with other types of drugs. So the idea is if you could get receptor subtype specific, maybe you could just fix the problem and not cause all the side effects. And actually, if you look at the idea of the opiate receptors, which is down below the bio at Davidson site, think about that. What do people take for pain? People take for pain morphine. Well, morphine is good, isn't it? But if you look at this picture, it turns out that there are 4 types of receptors for opiate drugs. And it turns out that when you take morphine, morphine binds to just about all 4 of them, and sure, it helps the pain, but it causes all of these side effects. Think if you were a drug company and you could create a molecule that just got bound to maybe the kappa receptors. Maybe you could fix the pain and not cause all the side effects. Can you imagine how much money that would be worth and how much help that would be? So this issue of receptor subtype seems to be very important. For any neurotransmitter now, they've identified that any neurotransmitter, there could be a number of receptor subtypes, and the thinking is if you could just fix this receptor, maybe you could fix just this behavior. The reason I bring it back up to you is because this idea is almost the idea of type reductionism. Do you remember that from way back in the beginning of this? Well, fix this receptor at a pharmacological level and then fix this behavior. If you believe in type reductionism, the idea of fixing neurons to fix behavior might be part of it. Of course, a lot of us don't necessarily believe that. We believe there's a relationship, token reductionism, but this is the idea of type reductionism. Going back to the story of the receptor subtypes, if you do those wiki searches, there's some interesting little facts about these neurotransmitters. And wiki, actually, somebody must have known what they were doing when they shared this information, because I printed it out, and actually it is pretty much correct. If you go to the nicotinic receptor, you will see, for this example of a subtype, I need my glasses here, that when acetylcholine binds to this receptor, and especially when nicotine does, that this receptor is right at the neuromuscular junction. And so it helps the muscles move a lot quicker. If certain things, like if you, what was I going to say here? If you read down on these channels some more, though, you can actually see that when they bind, they open up channels. They start talking about if you're bitten by a snake, neurotoxin, venom neurotoxin, actually blocks those channels. So that's a postsynaptic antagonist, and if it blocks the receptors, you can't move. Curare. When people take curare, curare is a nicotinic receptor antagonist. And when you take curare, it'll basically block the receptor here. And then think about what happens when you're hit with curare. Remember the original Indiana Jones movie? The bows and arrows, if the arrows had hit Indiana Jones, they had curare on it, they would have stopped the neuromuscular junction. So the acetylcholine receptor for nicotinic is basically at the neuromuscular junction, and it works with an ionotropic mechanism that opens up channels quickly and helps for movement. This is in comparison, so nicotine is the agonist and curare is the antagonist. Curare is, of course, used in terms of medicine these days. And actually, a lot of the things they give here are correct. The other receptor subtype is the muscarine receptor. And as it turns out, muscarine binds this. You can see the picture of the mushroom there. And as it says here, muscarine, when it binds, actually works with a second messenger system. So a metabotropic mechanism is one of the main things for muscarine. The other interesting thing, and I'll have a story here to end this off with, the antagonist for muscarine is something called atropine. Have you heard of atropine? Well, I'm going to take it back to one of my favorite stars from the 1970s and 80s. Do you remember Stevie Nicks of Fleetwood Mac? Does anybody remember? And I hope we have some older people in here. Her first solo album was called Belladonna. Belladonna. What people used to do way back when in Greek times is if you actually take a bit of atropine or belladonna, which is from the deadly nightshade, which is part of like tomatoes apparently, and you put this little bit in your eyes, it'll actually dilate the pupil. So women did it in Greek times to look beautiful. And of course, if you took too much of this atropine, it could kill you. So the idea is, it would be very much muscarinic tale. Stevie Nicks talked about it because you take something, it's beautiful, and then it kills you would be pretty much part of her symbolism. So atropine is part of this. You can read up on atropine as well. It works via a very different mechanism. So in summary then, and I've been babbling on for way too long here, the idea behind psychopharmacology. You should be able to talk about agonist and antagonist. The other term I didn't mention at the beginning but would be part of this would be affinity and efficacy. Affinity being how well does a neurotransmitter bind? Does a neurotransmitter have a strong affinity for a receptor? Does it bind well? And does it cause a lot of efficacy? So how well does it cause a biological effect? So we talked about that and gave examples, and then we went into this issue of receptor subtypes. The idea is, can you create a novel molecule that might help fix the problem and not cause all the side effects? That could be a receptor subtype. And then I went over this example of acetylcholine where you have one receptor subtype called the nicotinic. When you put nicotine in there, it has a high affinity and high efficacy. It'll really work well. Nicotine is, of course, blocked by curare, and it's at the neuromuscular junction and works ionotropically. On the other hand, you have the other receptor subtype, muscarine, or muscarinic. If you put muscarine in there, it'll bind really well to that. Atropine is its antagonist, and it'll have second messenger effects in different ways. So they're at different spots of the body, and this issue of psychopharmacology is a huge issue. So thank you very much for your time and your energy there.